Hello everyone, welcome to Gate Pass. In this video I am going to take problems related to thermodynamics which appeared in year 2008 GATE paper of chemical engineering. So the first question, it talks about a Carnot refrigerator which is operating between 40 degrees centigrade and 25 degrees centigrade, and they have asked you to calculate what will be the coefficient of performance for this refrigerator. Okay, so let's draw a schematic diagram. So your TH and TC, that is the temperature of the source and the sink, they are given. Okay, so your high temperature thermal reservoir is at 40 degrees centigrade. Convert it into Kelvin, so it will come out to be 313 Kelvin. Let's write it over here. So it is 313 Kelvin. And your low temperature reservoir, it is at 25 degrees centigrade, or converted into Kelvin, it will be 298 Kelvin. Okay. Now, since this is a refrigerator, it will lift heat from the low temperature reservoir and reject it at a higher temperature. Okay. So essentially, if this is my Carnot refrigerator, then it is lifting heat. Let's say it is lifting heat, QC amount of heat. Okay. And then you are doing certain work on it, W, and then it is rejecting QH amount of heat to the high temperature reservoir. Okay. So now coefficient of performance, it is usually defined as the desired output upon your input. Okay. So what is your desired output in this case? The desired output is the how much amount of heat you are lifting from a low temperature reservoir. So your desired output is QC. Okay. And what is your input? Input is the work which is done. Okay. So QC by W. So that will give you the coefficient of performance for your Carnot refrigerator. Okay. Now let's write W in terms of QC and QH. Okay. So from here you see that QH, that is equal to QC plus W, or I can write W is equal to QH minus QC. Okay. So let's write over here, instead of W it is QH minus QC. Okay. Let's divide the numerator and denominator by QC. What I get is 1 upon QH by QC minus 1. Okay. For a Carnot cycle, you know that you can write the ratio QH by QC as TH by TC, where the temperatures are in Kelvin scale. Okay. That's why we have converted the temperatures to Kelvin scale. So instead of QH by QC, I can write TH by TC. So this becomes 1 upon, what is TH? 313 Kelvin divided by QC, so that is TC, so divided by 298 minus 1, and if you do the calculation, what you get is the answer as your COP, that is equal to 19.866. So this is the right answer. So the next question which I am going to take, it asks you to calculate the work done by 1 mole of a van der Waals fluid which is undergoing a reversible isothermal expansion from initial volume Vi to Vf. 4 options have been given and you have to select the correct one. Okay, so first we will write down what is the van der Waals equation of state. So it is P plus A upon V square multiplied with V minus B, that is equal to RT. Okay, so this is your van der Waals equation of state. Since this question is taken from year 2008, where they never used to give the form of the equation which has to be used, but in recent papers you will see that most of the time they give you the equation of state which is to be used. Okay, but this is simply van der Waals equation which you can remember. Okay, so when a closed system is undergoing a reversible process, or I should say mechanically reversible process, then the work done on the system, that is usually given as minus of integral PDV. Since they have asked you to calculate the work done by the system, that is the work done by the fluid, so it will be positive. Okay, so work done now by the gas, that is equal to integral of PDV. You have to just evaluate this integral. Okay, for this we will write down the van der Waals equation of state explicitly in terms of P. So if you do that, what you get is P, that is equal to RT upon V minus B minus A upon V square. Okay, so this is your P. What I will do is I will plug it over here. So I have RT V minus B minus a upon v square, and I will integrate it from vi to vf. Okay, so you have to just evaluate this integral. Let's quickly evaluate this one and find out which is the correct answer. Okay, so it will be RT. Now if you take an integral, it will be ln of v minus b. Okay, and this will be minus a upon v square, so it will be okay. So plus a by v. So now you apply the limits. So from vi to vf, if I apply the limits, what do I get? RT ln vf minus b upon vi minus b plus a times, I should write over here, plus a times 1 upon vf minus 1 upon vi. So what do you see? Your option D is the correct one. Okay. So very simple problem. You have to just remember what is your van der Waals equation of state, and then just find out what will be the work done by evaluating this integral. Okay. So the next question which I am going to take, it talks about a liquid phase reaction taking place at 25 degrees centigrade. Okay, the standard gives free energy change of reaction and the enthalpy change of reaction at 298 Kelvin. It has been given. With this information, they have asked you to calculate what will be the value of equilibrium constant K at 95 degrees centigrade. 4 options have been given and you have to choose the right one. Okay, so the equation which we are going to use, that is Gibbs-Helmholtz equation. I had derived that equation in one of my previous videos. It was solution of 2012 thermodynamics questions part 2. Okay, so if you don't know how that equation comes, you can go and check that video. That was GATE Thermodynamics 2012 part 2. Okay, I am going to directly write down the equation which we are going to use. So it takes the form of dou by minus delta G0 by RT by dt by dou t, that is equal to delta H 0 upon RT square. Okay, so this is your equation. Now we know that minus delta G0 by RT, it is nothing but your ln K. So instead of this value, I can write dou of ln K. Okay, now I have to just integrate this equation from temperature T1 to T2. But before that, always remember to convert your temperatures into Kelvin. So your 25 degree centigrade is 298 Kelvin and your 95 degree centigrade, that will be equal to 368 Kelvin. Okay, so always remember to convert your temperatures into Kelvin, otherwise that is the only mistake you can make in this question. Okay, now integrate it. So if I integrate d ln K, that is equal to delta H0. So they have asked you to take delta H0 as constant upon R integral dt upon t square. If I integrate it and put the limits, so I go from K1 to K2. So here it will be T1 to T2. Okay, integrate this. What you get is ln of K2 by K1, that is equal to t square. So it will be minus 1 upon t, minus I am taking out. So it will be 1 upon T2 minus 1 upon T1. So this is the form of equation which you get. Now in this case, you have to find out K2, that is the value at 95 degrees. For that you have to first calculate what will be your K1. It's very straightforward. So how do you calculate your K1? K1 is equal to exponent of minus delta G0 by RT. Okay. So plug in everything. What is your delta G0? Minus 4650. So minus of it 8.314. What is the temperature? It is 298. If you do that, you get the value of K1 as 6.53. Okay. So I get the value as 6.53. I will put it over here, the value of 6.53, and then plug everything over here. So I will just erase some of the things from the board. Okay, now I will put everything. So K2, that will be equal to K1, that is 6.53 exponent of minus delta H0. So what is delta H0? That is 3640 divided by 8.314, 1 upon T2, that is how much is that? T2 368 minus 1 upon 298. Okay, and okay, yeah, everything done. So calculate this and you get the value of K2 as 4.94. So see which one of the options is correct. Option B is correct. Okay, so very straightforward question and very simple to solve. So the next problem, it gives you a binary mixture. So you have two species 1 and 2 with the mole fractions x1 and x2 respectively. So the molar volume V is given as a function of x1 and x2. They have asked you to calculate what will be the partial molar volume of species 2 when x2 is equal to 0.3. 4 options have been given and you have to choose the correct one. Okay. So we have done a similar problem in one of the previous videos, okay, but again we will derive the equation and use it over here. So let's write down the two equations which we use. So you know what is summability rule. So let's say that if your M is any extensive property, then I can write down my summability relation as, for a binary solution, x1 m1 bar plus x2 m2 bar. Okay, so this is my summability relation. Now let's take a differential of this. So what I get is x1 dm1 bar plus x2 dm2 bar plus m1 bar dx1 plus m2 bar dx2. Okay, so this is the, I am just differentiating this equation to reach this. Now x1 dm1 bar plus x2 dm2 bar, that is equal to 0. And how it is 0? From your Gibbs-Duhem equation. Okay, so these terms go to 0. Then what I am left with is dm, that is equal to m1 bar dx1 plus m2 bar dx2. Now since this is a binary solution, I know that my x2, that is equal to 1 minus x1, or I can write dx2 is equal to minus dx1. So instead of dx2 I can write minus dx1. So I take dx1, if I take common, then I can write m1 bar minus m2 bar dx1, or I can write dm by dx1, that is equal to m1 bar minus m2 bar. Okay, so I am going to retain just this equation on the board and then erase everything else. Okay, so I have this equation and then further I have dm by dx1, that is equal to m1 bar minus m2 bar. Okay, now since I have to find out m2 bar, so I will eliminate x2. So what I will do is I will write x1 m1 bar plus x2 I can write as 1 minus x1 m2 bar. Okay, now take x1 common, so you get m1 bar and from here you will get m2 bar plus m2 bar. Okay, now rearrange this equation, solve for m2 bar. What you get is m minus x1. Now m1 bar minus m2 bar is nothing but dm by dx1. Okay, so this is the equation which we are going to use. So it's very simple equation, you can remember it, or else if you don't remember it, don't leave this equation, this question, you can derive it within 2 minutes. Okay, so this is your equation. Now I will erase everything and write this equation in terms of my molar volume which is given. So V2 bar, that is equal to V minus x1 dV upon dx1. Okay, so with the rest of the problem, it's very simple. Now let's first evaluate what will be V when x2 is equal to 0.3. Okay, put the value of x1 as 0.7 and x2 as 0.3. Do the calculation and what you get is that your V when your x2 is equal to 0.3. Do the calculation and first evaluate this thing. So what I get is basically 224.38. Okay, so this is the first term in this equation. Now I am going to evaluate what will be dV by dx1. Okay, so B is given over here. I will simplify this equation a little bit, because x2 I have to write in terms of x1. Okay, so I can write 220x1 plus 180. x2 is 1 minus x1. Okay, so you will get 220x1 minus 180x1, so it will be 40x1, and you will have plus 180. Okay, plus it will be x2 x1 square multiplied with 90 plus 50 x1 x2 square. Okay, now I am going to take a differential of this. So dv by dx1, so it will be 40. This will give you 0 plus, now I will apply chain rule. So okay, first I will differentiate this term x1 square, so 90 times x2, the differential of this will be 2x1, so I can write this as 180 x1. Okay, next I am going to keep x1 square constant, x2 that is 1 minus x1, if you take a differential it will be minus 1. Okay, so it will be minus 90 x1 square plus, let's do that. Let's first keep x2 square constant and differentiate x1 1, so 50 x2 square. Then I am going to do okay, differentiate x2 square, so that is 1 minus x1 whole square, differentiated it will be 2 into 1 minus x1, and there will be a minus sign, so 2 times minus 1, so multiply it with 2, so it will be 100, and 1 minus x1 it will take the form x2. Okay, so this is your differential of v with respect to x1. Okay, most of the things you can do mentally, so I have not written all those steps, but I have walked you through how you calculate your dv by dx1. Now put the values of x1 and x2 in this, and what you get is that, so your x1 is 0.7 and x2 is 0.3. If you put these values, then you can calculate dv by dx1 at x2 equal to 0.3, and the value comes out to be 17.2. Now everything else is simple. v2 bar at x2 equal to 0.3 is 224.38 minus x1, that is 0.7 multiplied with 17.2. Okay, so do the calculation and you get 212.34, which is the answer. So this option B is correct. Okay, very simple problem. Don't make a mistake while taking the derivative and putting in the values of x1 and x2. So nothing else in this problem. You have to reach just this equation. You can remember this equation, or you can also derive this equation. So the next problem which I am going to take, it says that you have a binary mixture which contains species 1 and 2, and it forms an azeotrope at 105.4 degrees centigrade and the pressure of 1.013 bar. The liquid phase mole fraction of component 1 is 0.62 at 105.4 degrees centigrade. The pure component vapor pressure of species 1 and species 2 have been given. So these are the saturation pressures at the temperature at which the azeotrope is formed. Okay, so these vapor pressures have been given, or the saturation pressures have been given. Now they have asked you to calculate what will be the value of your activity coefficients gamma 1 and gamma 2, and further they have asked you that if your Van Laar constants are given by these equations, then find the value of A and B. Okay, so equation is given for A and B. It is in terms of your mole fractions and your activity coefficients. So first step is to calculate your activity coefficients. Okay, it's very simple. So let's go through this problem. So if you have x1 equal to 0.62, then your x2 will be equal to 0.38, because this is a binary mixture. Now since it is forming an azeotrope, that means it's a constant boiling mixture, so your vapor phase composition will be same as your liquid phase composition. So my y1 will be equal to again 0.62 and my y2 will be equal to 0.38. Okay, now it's a very straightforward problem. In order to calculate your activity coefficients, I am going to use my modified Raoult's law. How it is written? It is y1 total pressure P, that is equal to x1 gamma 1 P1 saturation. Okay, similarly y2 P, that is equal to x2 gamma 2 P2 saturation. Okay, at azeotropic condition, your x1 is equal to y1, so these terms will go away, okay, from both the equations. Now what you are left with is only these quantities. Now you know what is the total pressure, you know what are the saturation pressures. Quickly you can go and calculate your gamma 1, that will be equal to P upon P1 saturation. So that will be what? My P is 1.013 bar divided by P1 saturation, so 0.878, and over here that will be 1.013 divided by 0.665. So my gamma 1 1.153 and your gamma 2, okay, I should write this as gamma 2. Okay, so my gamma 2, that will be equal to P upon P2 saturation, and the value is 1.523. Okay, so I have now obtained my values of gamma 1 and gamma 2. Now I have to just plug in these values over here and evaluate the values of A and B. You can do that, and it's very simple, just plugging in the values and do the calculation. You get A as 1.124 and B, that is equal to 1.01. Okay, so very simple problem, even though it looks a little complicated to start with, but you have to just know what is your Raoult's law. Okay, apply that, find out your activity coefficients. Remaining things are very simple, just plug in and evaluate the value of A and B. So please don't forget to subscribe to my channel and like this video, and thanks for watching.